Chapter 14. I'm dividing this one up into a couple different sections, into a couple different, parts, because just such a big one. Okay, so this is so important for the next couple chapters that I want to give this section a lot of attention, or the attention that it deserves. Okay, so the question that we asked in the beginning of the first video for this section was, can we, or rather not, it's not a question, we can figure out the equilibrium constant Kc if we know all the concentrations of the components at equilibrium. If that's true, can we figure out the concentrations of the components at equilibrium if we know the equilibrium constant, right? So we're still working on that question, this question down here. And we looked at a simple scenario in the last video where we knew the concentrations of everything except one. Now let's look at a scenario where we don't know the concentrations of everything, and this is going to be more realistic. So suppose you've got some reaction. A is in equilibrium with 2B. All right, you've seen this from a previous section, how we did this, right? If we start out with 0B, then we know we're going to be gaining some, right? And whatever we gain here, we have to lose over here. So we're going to be losing some from A. And since it's a 1 to 2 ratio, can you see that? The coefficient's 1 to 2. I'm going to call this X, right? So we're going to lose X from 1. And that's where this comes from. And if we're losing X from here, we're going to gain 2X over here. And so 0 plus 2x is going to give you 2x. Well, this is great, right? We know that K is equal to products over reactants, right? Which in this case is the concentration of B squared over the concentration of A, right? Because that's, all right, it's going to be squared. If that's true, now we can simply say, well, this must be, the change must be 2x squared over 1.0 minus x. Right? Oh, I only have one variable here. I can solve this. Right? You see that? I can solve it. And so it turns out that's what we're going to do, solve for x. Solve for x. And that's all we're doing here. Okay, so let's do an example. We'll see that there's going to be some situations in which this is very simple and some in which it's not so simple. So let's look at 3 different possibilities here. First of all, suppose we've got nitrogen gas and it's combining with oxygen gas in equilibrium to give 2 moles of nitric oxide, or nitrogen monoxide, as we would have named that in section 3.5. Okay, and it's got some Kc that's given here, 0.10. Okay, so now look at, if we're starting with 0 nitrogen monoxide, then we know we must be gaining some, and to change, right? The change is going to have to gain. If that's going to gain, this is going to be a loss. All right, and it looks like this is a 1 to 1 to 2 ratio, because this coefficient here is 1, right? That's 1 and this one's 2. Okay, so it's a 1 to 1 to 2 ratio. So I'm going to say, let's suppose that's minus x, and that's minus x. And this will be then plus 2x. Okay, so the equilibrium amount then is going to be 0.200 minus x, 0.200 minus x, and 0 plus 2x, right? But I'm just going to write 2x. You see that? So that's how we do the ICE table. Aha, ICE table. That's how we do the ICE table for a problem that looks like this. Okay? So let's look at another example of this. Suppose we've got dinitrogen tetroxide. Dinitrogen tetroxide is in equilibrium with 2 moles of nitrogen dioxide. Okay? Now let's suppose that we start out with 0 of the dinitrogen tetroxide is 0, and so it looks at equilibrium we're going to gain some of that, right? You know, at equilibrium you're not going to have 0, right? So if we're gaining that, we're going to be losing this. Now this is a 1 to 2 ratio, so let's say that we're going to be gaining x and losing 2x. Can you see there's my 2? So at equilibrium, my equilibrium concentrations of this are going to be 0 plus x, which I'm just going to call x, and 0.100 minus 2x, right? And can you see then I'm ready to set my equilibrium constant up. This is going to be NO2, looks like that's squared, over dinitrogen tetroxide. Okay, and the equilibrium concentrations are going to be 0.100 minus 2x squared over x squared. Right? You see that? Oh, no, that's not squared. Sorry, that's not squared. I'm sorry. This is just going to be x. All right, so let's do a specific example now. This is example 14.9. It's in your textbook on page 581. You know, Trove worked these out too, right? You've seen that. So consider the following. I'm only doing this because sometimes the students prefer to have somebody walk them through it. So that's what I'm doing here, okay? So consider the following reaction. Nitrogen gas plus oxygen gas gives 2 nitrogen monoxide, okay? This is K. A reaction mixture initially at 2,000 degrees Celsius, which doesn't really matter except you can see you're at the right temperature for this equilibrium. Initially, okay, so initial, N2, O2 is in equilibrium with 2NO. I'm going to set my ice table up right below that. I, C, E. Okay, initially contains nitrogen at 0.2 and oxygen at 0.2 and probably 0 nitrogen dioxide. A reaction mixture initially contains just this stuff. Okay, so it's going to be 0. All right, find the equilibrium concentrations of the reactants and products at this temperature. Okay, so it looks like, and this is a 1 to 1 to 2 ratio, right? So this is going to be gaining because it's not going to have 0 at the end. So if that's gaining, this is going to be losing, and this is going to be losing. And it's a 1 to 1 to 2 ratio. So I'm going to say minus 1x minus x plus 2x. Okay? So this equilibrium concentration is going to be 0.200 minus x. This one is going to be 0.200 minus x. And this is going to be 0 plus 2x, which I'm just going to write as 2x. Agreed? So the equilibrium, the concentration of these at equilibrium is going to be, what do I have here? Nitrogen monoxide squared. Okay, this we've done enough that perhaps you're comfortable with it. Okay, and NO at equilibrium is going to be 2x squared. And these are going to be 0.200 minus x, 0.200 minus x. So it looks like that's also squared, right? 2x squared, because these are the same. 0.200 minus x squared is equal to k. All right, so let me come up here now. I'm going to continue on the other side of this page. I can just take the square root of both sides and find out that the square root of k is equal to 2x over 0.200 minus x. Agreed? Let me solve for x now. I multiply both sides by that mess. Minus x times the square root of a is equal to 2x. square root of k. I don't know what I just said there. I'm going to distribute that out. Root k minus x root k is equal to 2x. And get all my x's on the same side. 0, 0 root k is equal to 2x plus x root k. I'm going to pull out the x. X is equal to 2 plus root k. So it looks like x then is going to be 0.200 root k over 2 plus root k. I'm going to put all my numbers in now. What is k? 0.1? Okay, now I'm going to put that in my calculator, and I am going to find that gives me x is equal to 0.27. Oops, no, 0.027. 0.027. Okay, I don't have enough room here. Didn't leave myself enough room. 0.027. Now, if that's true, then my equilibrium concentration of nitrogen N2 0 minus 0.027, which is equal to 0. I can't do this in my head. 1.73. 1.73. Okay. And oxygen is going to be the same. 173, and this is molar. Molar, can you see where I got this? I got this from here, and this, too, I got from over here. Because the question was, what is it at equilibrium? Find the equilibrium concentrations, and that's what it is at equilibrium. Okay, for nitrogen and for oxygen, there's nitrogen, there's oxygen, and finally I've got to do nitrogen monoxide, which is 2x, okay? And so if x is 0.027, nitrogen monoxide is 2 times 0.027, which is equal to, oh, I don't know, what is that? 0.054 molar, okay? And that's my last one. So if that's the answer, let me make sure, or rather those are the equilibrium concentrations. Let me make sure I answered that correctly. Find the equilibrium concentrations of the reactants and products at this temperature, which I have done. QED. Quod erat demonstrandum. Okay, so let's do another example. This next one is a little more elaborate. Okay, so find, you'll see, it looks simple here, but you'll find it's got its challenges, okay? So I'm going to leave myself some more room. Let me divide the page up here into 3 sections, and I'm going to obey those sections carefully. N2O4 is in equilibrium with 2NO2. I'm going to write the equilibrium expression up here. It's NO2 squared over N2O4. You know why that's squared, don't you? Okay, we've been doing this a good bit. Hopefully that's clear to you. Okay, so I'm going to do my ICE table over here, ICE. A reaction mixture at 100 degrees Celsius. Oh no. This has got to be a mistake. This is a mistake. There's no way that this, look at this, 100 degrees Celsius, 2,000 degrees Celsius. This 2,000 surely comes from the past problem here. This is a typo. Right, because we're not talking about temperature at all in this section, right? So that's typographical error. So suppose that this says 100 degrees Celsius, or that this one says 2,000. A reaction mixture at 100 degrees Celsius initially contains this much of NO2, nitrogen dioxide. So initial is 0.100, and that's all it does, okay? A reaction mixture, and that's all it's got. So this must be 0. Find the equilibrium concentrations of these two guys, okay? So if this starts out at 0, this must increase, right? And it must come from this side. And this is a 1:2 ratio. So let's say that this, for every 2 moles that gets loses, this gains a mole. All right? So it looks like your equilibrium concentration of dinitrogen tetroxide is going to be X, and this is going to be 0.100 minus 2x. Okay? Well, we've got the expression up here. So I'm going to say K is equal to nitrogen dioxide squared. So that looks like that's 0.100 minus 2x squared over dinitrogen tetroxide, which is just X. Uh-oh. Okay. Well, if this is the case, then I've got to solve for X, right? It looks simple enough, but I'm going to go ahead and do this now. I can't take the square root of both of this side because only the top term is squared, so it's going to be a quadratic. So it looks like it's going to be Kx is equal to 0.100 minus 2x squared. Oh man, I gotta FOIL this, okay? 1 minus 0.2x minus 0.2x plus 4x squared. Okay, which is equal to 0.01 minus 0.4x plus 4x squared. That's what Kx is, okay? Now, I have a quadratic. And in order to solve this, I'm going to go ahead and simplify it and put it in terms of the regular quadratic equation first. So all x terms, of course, have to be on one side. And usually when we do that, we say 4x squared. I'm going to put that first. Minus 0.4x minus kx plus 0.01 is equal to 0, right? Because I'm looking for the general form for a quadratic. The quadratic equation, ax squared plus bx plus c is equal to 0. X is given as minus b plus or minus the square root of b squared minus 4ac all over 2a, right? So I have to set up in this form first in order for it to solve this as a quadratic. All right, so if that's the case, and I've got it here, it looks like A is equal to what? What's A equal to? 4, right? There's my A term. B is minus 0.4 minus K, which I'll solve. Well, let's solve that now. Minus 0.4 minus K is 0.36. Minus 0.76. All right. And C is equal to what? Where's my C term? Right there. 0.01. Okay. So then I put it in my quadratic equation up here, which I'm not going to write all out. I've written it up here. X must be minus b plus or minus the square root of b squared minus 4a ac all over 2a. So if I do this, you see my plus or minus, this is going to give me two answers. And the one answer is 0.176, and the other answer is 0.014. These are my two answers, okay? Now, one of them doesn't make any sense. And I want you to stop. Really, what you ought to do is you ought to pause the video at this point and ask yourself, why does this not make any sense? It turns out this one doesn't make any sense. Actually, I'm not even going to tell you. I want you to look at that, pause the video, plug that into your initial stuff over here, and see why does that not make sense. Okay? So since it doesn't make sense, we're going to say, I'm going to change color here for a second. You can't see that. I'm going to go over here to blue. To blue, you're going to go, whoa, that doesn't make sense. Okay. Go back to red here. Okay, now we're going to find that x is, this is the only thing it can be. And so the equilibrium concentrations of these are going to be N2O4 is going to be x, which is 0.014 molar. And the concentration of nitrogen dioxide, I'm gonna put a box around this, okay? That's my one answer. And then my other answer is going to be 0.100 minus 2x, which is 0.014, 100 minus 2, or rather, what's that? 2 times that, 0.028, which is equal to, I can't do this in my head. I can't do that in my head, sorry. 0.1 minus 0.028 equals 0.072. 0.072 molar. And that is my other answer. Okay, so let me come here, circle that, and we'll be done with this. All right, so here's the challenge with this one. I think the ice table, you know, after you do ice tables a good bit, you're going to like them. So that's not a big deal. I mean, yeah, okay, so you don't like it yet. I get that. But you'll like it. You've got to practice it, and when you do, you'll be good. But the challenge here, then, I think, is getting yourself a quadratic. And I would say, you know, this is something you did successfully in a prerequisite course. You had to do the quadratic equation in order to pass the course that was prerequisite for the course you're in right now. So you've done this before. But we don't do it often enough to be comfortable with it. Okay? So I'm going to suggest, I'm going to put a little blue mark next to the part that I think is going to be the scariest. And it is right here. And right here. Right? All that right there. The quadratic. Okay. So that's a mess. Now, the last video I do for this section, we're going to find that we can skip that part, usually. But if you have to do it, if you can't skip it, then this is where you are, and you're going to end up, I think this is worth, a picture's worth 1,000 words, right? And maybe some tears coming off. This is you. Okay? All right, so Let's do one more problem here. I think this next one's going to be a little easier. We've been doing these in terms of concentrations. Let's do this one in terms of pressures. So I'm going to do the same thing I did before. I don't think I need 3 panels here. Mind if I switch to blue for pressures? Nah. We went with red. Let's go with red. Okay, so I2 plus chlorine gas is in equilibrium with iodine monochloride. Okay? Oops. 2. Big deal. Initial change equilibrium. So a reaction mixture initially, okay, see 25 degrees Celsius. Okay. So the reaction mixture initially at, 25 degrees, initially contains partial pressure of I2 of 0.1 atmospheres, 0.100 atmospheres, and partial pressure of chlorine gas of 0.100 atmospheres. And, oh, wow, okay, so we've got 0.100. Find the equilibrium partial pressures. All right, so here it's not really obvious which side is going to be gaining, except I do know this. Watch. K is equal to the partial pressure of ICl squared over the partial pressure of, iodine times the partial pressure of chlorine. Okay? And I see that this K is bigger than 1. But if I was doing my reaction quotient, yeah, we can do that. It'd be a great time to practice this, wouldn't it? I know this is getting a little bit ugly here, but my reaction quotient is got the same expression, right? And it's at 0.1 squared, right? Because that's what this is, over, and these are both 0.1, so it's also 0.1 squared, which is equal to 1, right? So since Q is lower than K, it looks like I don't have enough products, so I'm going to be gaining products over here and losing these guys. You see what I just did there with Q? Okay. Now, if that's the case, it looks like this is a 1:1 to 2 ratio. So if I lose x here and lose x here, I'm going to be gaining 2x, right? And so this equilibrium amount is 0.100 minus x. This is the same. I guess I'll write it out. 0 minus x, and this is 100 plus 2x. Okay? And I've got my, did I call that concentration? These are my partial pressures. Did I, you heard me say this, right? We already have that. And so K is going to equal 0.100 plus 2x squared, right? Because that's what this is. I'm going to put a 1 here and a 1 here. You see where that comes from? It's like a little footnote there, okay? 2, 2, 3, 3. You see that? Okay, so this, and these are the same, right? So this is going to be 0.100 minus x squared. Agreed? So I can take the square root of both sides now, and this then will be the square root of k is equal to 0.100 plus 2x over 0.100 minus x, and I no longer have any squared terms in here. So I don't need the quadratic equation for this. I'm going to solve this. 0.100 minus x times root k, 0.100 plus 2x, okay? So 0.100 root k minus x root k is equal to 0.100 plus 2x. I got to get my x terms together. So I'm going to switch this guy around. Do you mind if I put 2x over here? 2x plus x root k, right? Because I just switched this thing around and then added x root k to both sides. How do you spell k? With a 2? Plus x root k is equal to 0.100 root k minus 0.100. Okay? I'm going to pull the x out. 2 plus root k minus 0.100. X then is going to be 0.100 root k minus 0.100 over 2 plus root k. All right, why am I doing that? Root k. All right, so x then is going to equal 0.100. Now I'll put root k in. It's root tempted to say that's like it's close to the square root of 9, or 9, right? Because 81 is the square root of 81 is 9. That minus 0.100 over 2 plus root k. 9. I'm going to solve this little by little now. And oftentimes I put this all in my calculator all at once. But just a second here. 81.9 square root times 0.1. This goes to be 0.90499 minus 0.100, 2 plus just a second here, 9.0499, right, is equal to 0.80499 over 11.0499. I think that's right. We'll check this carefully here in the end, okay, and make sure this makes some sense. So that times 0.1 equals 0.9049 minus 0.1 equals, okay, divided by 11.0499 equals 0.0729, okay? 0.0729. That's what x equals, all right? So if x equals that, then the equilibrium concentrations, what was I supposed to do? Find the equilibrium partial pressures, sorry. Find the equilibrium partial pressures of all three of those. So the concentration of these two is going to be the same. I2, Cl2, it's 0.1 minus x. And I'm not going to write that all out. I'm going to simply do that there. Plus 0.1 equals, should be 0.027. And we've got 3 sig figs and all these things. I'm not going to walk through each of those. I think it's going to end up with just 3 sig figs. Atmospheres, right? And then the other one is going to be, what is the other one? I said concentrations. These are partial pressures, sorry. This should be the partial pressure of Cl2, okay? And the partial pressure of ICl is equal to 0.1, clear, 0.1 plus, just a second here, 2 times, and what was x? .0729, 0.0729 equals plus 0.1 equals, ought to be 0.2458. 0.24 and 3 sig figs is going to make that 6 atmospheres. All right, so there's our answers. That, I think, is accessible to you. If students are going to get lost here, it may be in the algebra, which, of course, has to be practiced. So even if it looks easy, it's still as easy to get sideways on that. But I'm pretty sure those are right. Okay, so those are this is for section 14.8 part B. And now for section 14.8 part C, we're going to show how we can make an approximation and simplify some of these problems. Not all of them, but